All right, we're gonna get started. Welcome back, everybody. Thanks for being flexible with the whole week off there right after spring break. Hope you guys were able to enjoy your spring break a little bit and have some catch-up time. And hope it doesn't come too much of a surprise that we have an exam this week. I'm sorry it just lined up that way. But yeah, today we're going to be reviewing the homework and then also the practice problems. If you didn't get a chance to look those through yet, it's okay. I'm going to try to go through the step by step a little bit slower. So I will also post this lecture as soon as it is finished uploading later today. So you get a chance to go through it, you know, in a little bit, you change the time and stuff. But yeah, so exam is going to be on Thursday. Going to be covering lectures 8 through 14, everything highlighted in blue on your syllabus. Again, sorry for that break between everything, but pretty much everything before spring break. And also there will be some conceptual questions on the online tools that were from last week's videos that are going to be on there. Nothing serious. Hopefully you guys all got a chance to review those and take that quiz and just understand the basic concepts on those three tools: Google Earth, historical images, USDA, and then FDOT. So those four tools. As I mentioned in those videos, you will be using those tools, those online tools, as part of your final lab. One other thing I need to mention, the lab I think is supposed to start next week. I may have to cancel that. I'll keep you guys updated on that. Yeah, I might need to take a trip for a family funeral, unfortunately, next week. And I'm going to try to get back here for Tuesday, but I may have to cancel next Tuesday's class and do a video, which means I'll probably have to push the labs back again. So we're still trying to figure out flight details and stuff, but I'll keep you guys posted on that. Just wanted to give you a heads up. So any questions on where we're at in the schedule right now? I'll go over more details on the exam format on the next slide, but is there any concerns or issues just right off the bat? Is anyone awake? No. That makes 40 of us. All right, well, we'll go through this slowly. And if there's any questions or anything comes up, please let me know, raise your hand and we'll get it sorted out. So exam format's going to be pretty much identical to your exam one. Closed notes, closed books here in class. It's going to be same questions-ish. There is going to be more stuff just since we've done more calculations, and so less concepts. There's going to be more multiple choice that are actual fill in with an answer instead of knowing a concept. So I feel like a lot of you guys will probably like that. More opportunities for partial credit. Same amount of questions though, so it's just going to be weighted a little bit differently. As you guys have known probably from your exam one, definitely recommend writing anything and just working on those partial credit questions at the end. If those are blank, then I can't do anything. But if I at least see you working through and thinking through how to solve this or solve those questions, then I can at least, award some points. I mean, you guys have known by now, a lot of these engineering classes are they require a lot of thinking and a lot of design steps. So what I want to see most of all is your understanding of at least the basic concepts and how to apply it. Even if you can't fill in that gap and you're missing one little piece of information, as long as I see that you know the big scheme of things and you at least understand how to get from point A to point B, even though you don't have all those points in between, that's at least what I'm looking for in a lot of these. So fill out those partial credits a lot more. There's going to be similar to your first exam, there is that first page is going to have just random things on it that you might need that I don't expect you to memorize. One being the prefixes for the SI stuff. So what you'll have is, the prefixes table for the SI or SI units. So I don't expect you to memorize those. You'll also have basic flow chart for the classifications. So I'm not going to ask you like a giant question, like how to find a classification, like a soil classification from start to finish. But what you will need to know is at least the basic like identifiers for USCS and AASHTO. So like if a soil is greater than 50% passing the number 200 sieve, then that is a fine grained soil. Like you're going to need to at least know that. Like you won't need to know and memorize the entire flow chart, but you'll need to at least like be able to identify by looking at a sieve, like a grain size distribution, whether it is a coarse grain soil or a sand or a fine grain soil, you know. So just to recap those, if for USCS, passing the 200 is greater than 50%, then that is a fine grain soil. 200 sieve is really important. If minus the 4 sieve is greater than, yeah, so let me say number 4 sieve. So this is the differentiation between gravel versus like sand. So number 400 or number 4 sieve and the number 200 sieve, you need to at least understand those basic things of how we identify whether it is a gravel, fine grained, or sand, and something in that. All those little in between things, don't worry about that. So just like before, bring a pencil, bring a calculator, bring scrap paper if you need to, and then you'll submit everything. And yeah, any questions on format? Okay. All right, let's go through some of the homework problems. A lot of these kind of move a little bit quicker because hopefully you've had some time to review those and ask me questions already. But we have something like this. You have the sieve number, the percent passing. That is what makes up our grain size distribution curve. But we have to remember that the number corresponds with an actual millimeter size. So you aren't expected to memorize each one of those, but what you should know is that the number 200 sieve, the number 4 sieve is 4.75 millimeters, and you should know that the number 200 sieve is 0.075 millimeters. So those should just be like rules of thumbs, like drilled in your mind for geotech and for materials. Those are the two most important sieves. Number 4, 4.75, number 200 is 0.075 millimeters. And remember, if you can't remember those two numbers, remember what that number actually represents. The number, so number 200 means there is 200 opening sizes per 1 inch of sieve. So like you can do the math in your head and kind of check it out. You know, obviously it's going to be a little off because there's thickness of the wire gauges and everything. But that's a good way to at least like remember the generalized trend. The higher the number, so number 200 means there's more openings per 1 inch, which means the opening size has to be smaller, right? So number 4 sieve means there is 4 openings for 1 inch. Number 200 sieve means there's 200 openings per 1 inch, so smaller. So try to remember those. All the other like sieve numbers you don't need to memorize, but for this one, you know, you can plot everything for the homework. And then we plot the x-axis being grain size in log scale, and then the y-axis being the percent passing in linear scale. I should note this percent passing is also sometimes shown as percent finer. Just depends on who you're talking to. So sometimes you might see a plot that shows it as percent finer. Same thing, but your plot should look something like this. And first thing you'd notice right off the bat is that we don't really have a lot of information for this. And it's probably apparent down here when you start looking at percent passing. you know the classification system, if we have greater than 50% passing the number 200 sieve, then we have a fine grained soil, which means it's either a clay or a silt. And in this case, we would then need to do the hydrometer analysis to have this additional curve here, right? So that's from the hydrometer. So you're not given this information. We're given the plasticity. We're given these values as well from our Atterberg test. So we can find our plasticity index. Plasticity index is always the subtraction of the two limits. So this is really important. A lot of times I see this as a mistake here. Index is liquid limit, which is a higher number, minus the plasticity limit, which is the lower number. And so we can do that math and find that our plastic index, is 14%. So the other ones, the soil coefficient of curvature and the soil's coefficient of uniformity, those are these equations. These are meant for coarse grained soils. And for that, we need a full curve. We need to find our D60 and our D10. So how you would normally read that is the percent passing here. Our D60 you would read over, and wherever it intersects with our curve, you would read down, and this would be our D60, for example. But you'll see for this one, our D10, we don't have enough information. And that is, again, because we're missing the hydrometer there. So this was kind of meant to make you guys think a little bit. This is a fine grained soil, and for the fine grained soil, we need further testing to define the coefficient of curvature and the coefficient of uniformity. So for these, we have not enough info. So you guys know on my quizzes and stuff, I have like all those, like the part D sometimes being not enough information. And most of the time it's not that. In this case, this would be a case, or this would be an example where, we honestly don't have enough information to find this. So you would need to recognize this. This is a common question on the FE and on the P. Well, I didn't see it on the PE, but I remember it on the FE at least, like them giving you this curve and then trying to find this. And you have all these numbers and you're spending all this time calculating it, but then you have to recognize that, oh, this is a coarse grained soil or a fine grained soil, and we wouldn't be able to find those CU and CC from that. So even without that though, we can still determine the USCS classification. So we know that our PI is 14%. And so let's go through some of the steps here. So we know that there is greater than 50% passing the 200 sieve. So again, this is something that I would highly recommend you guys memorizing. That 200 sieve is, it's pretty easy. It's whatever the majority is. So if the majority is passing the 200 sieve, then we know it is considered a fine grained soil. So that means it's either going to be clay or silt. Those are our two fine grained soils. So we know the first group symbol is going to either be a C or an M, C for clay, M for silt, for some Latin word for silt or Greek word for silt. And then we want to look at the liquid limit. So that liquid limit is the thing that differentiates between high or low plasticity. So whether it's going to be a H or an L. So if the liquid limit is less than 50%, that means it is low plasticity. So remember, this chart is based off of the 1940s, super empirical, low amount of data. They just said a straight line on the liquid limit separates the high plasticity versus the low plasticity. So 50%, or if we look at our chart here, let me go back actually. So that means it's either going to be the options that we have are going to be a CL or an ML in this case. So if we look at our flow chart, and again, I'm not going to be giving you this exactly. You don't need to memorize all of these things. But if we look at our flow chart, we would have greater than 50% passing the number 50 sieve or the number 200 sieve. There was no identification of organics. The liquid limit is less than 50%. So it would be one of these options. And what we need to do is look at the Casagrande chart. So the Casagrande chart, it would always be provided to you on the test, so you don't need to memorize that or anything. So if we see here, it's a function of plasticity index, so PI on the y-axis. and then liquid limit on the x-axis. So if we tried to read this, 43 would be somewhere about here. Our PI would be 14, which would be somewhere here. We'll see that this chart is actually very difficult to read. We can't discern exactly where that is. It's right on the threshold. So luckily we have functions for these lines. So we know that this A line here, the thing that separates a CL versus an ML, is this function here. So PI is equal to 0.73 times the liquid limit minus 20. So what we need to do is plug our liquid limit in and then determine whether that PI is greater than or less than this function, our current PI. So what we can do is plug in our values. We know our PI is 14%, that's calculated. And our liquid limit is 43. That's given to us here. So 43 minus 20 times 0.73, we see that 16.8%. So is this above or below the A line? This is greater than 14%. So that means our current PI is below our A line. And this might, like, think about this, like, you know, because it's a little counterintuitive at first. This means that this A line at our 43 right here is at 16.8%. 16.8%. But our data point is 14%. So if that 14 is less than 16, then that means we are under that A line, that function. So that means that our soil is an ML since we are under that A line. So don't always rely on your eyeballs when you're reading this thing. Like, you know, sometimes that might be really close to the function and you need to actually plug it in to the equation and then determine that. One other thing to remember, what happens if we have data in here? What is this? This section above our U line. What does that mean? Does anyone remember? Yeah, it means you messed up somewhere. So go back and double check stuff because you should never have a data point in there. Most of the time, if you have a data point in there, that means you're using the plastic limit on your y-axis instead of the plastic index. So double check that. Like if you're in a rush and you're going through it, always double check and make sure that you're using your plastic index on your y-axis. Okay, so we still need to find the group symbol and the group name. So from that, again, you don't need to memorize this stuff, but I'm at least going to go over it for the homework. From lecture 9, you have this lovely table here. We know that it is an ML. So everything else we can forget about. And what we want to do is now just follow this flow chart. So if we have greater than, I should say the plus, what we know is that there's 55% passing the number 200 sieve. That means there is 45% retained on the 200 sieve. And where there's also 95% passing the 200 or number 4 sieve. So that means there is 5% retained on the 4 sieve. That means the percent gravel is 5%. So from this, we can flow through everything else here. Remember that the plus is meaning retained in this table. So we have 45% retained on the number 200 sieve. So that means we come down here. We have 40% gravel, or sorry, 5% gravel and 40% sand. So our percent sand is greater than our percent gravel. Let me just go through this way here. So this is what we have, and then we're going up here. And then we have 5% gravel, which is less than 15%. So we're over here. And that means we have just a ML. And what we would call it is a sandy silt. So why do we go through this whole step again? Like all of this to just call something a sandy silt. Who remembers? What was that? Find the strength. Yes, it is correlated, but why else? Like big picture. Like if I like have this now a sandy silt and I call my friend in Colorado and I'm like, hey, I got a sandy silt, like he's gonna know exactly what it is, right? Like this is the whole thing with the unified soil classification. So exactly what you were saying though, Ariane, like we have this now unified way of speaking and knowing what a sandy silt is. So now correlations, strength correlations or other statistics, any type of empirical like relationship developed for a sandy silt soil can then be used throughout the world because that sandy silt soil is going to behave the same. So if we didn't have this, pain in the butt way of trying to find like the terminology, then we'd all be speaking different languages and nothing would get done like to progress the field on like a world and international scale. Okay, so soil classifications, that was the USCS one. Now we have the AASHTO. And remember, what's the big difference? When would we use AASHTO versus USCS? Roadways, yeah. So any roadway project. What about if you were doing like a roadway bridge, like an overpass? What would you use? Yeah. So that's the tricky part. Like even though it's a roadway, any structure on the road, like a retaining wall or a bridge, or even like those toll gantries, those big like signs that are like really like 20 feet tall that you say like JTB on it and stuff. Like any type of structure near the road still uses USCS. So just the roadway subgrade and like the typical driving lane and stuff, that is used for AASHTO. So we're going to do the same thing, classify soil using AASHTO classification, provide the group number, the group index, and then I ask a random question, would you recommend the soil to be used as the roadway subbase? So the AASHTO flow chart looks like this. The big difference between AASHTO and USCS, besides the application, is the differentiation here on the 200 sieve. So where the USCS says 50% is that dividing line, the AASHTO people say 35% is that dividing line. So that's a major or an important difference between these two. So this is from your lecture 10. What we're given from before, we know that 55% is passing the number 200 sieve. So that means we're only going to look at the left side here since there is more than 35% passing. We're given the PI is 14%. So that is greater than 11. So that means it is a clay. So that is this area. And then we look at the liquid limit. The liquid limit is 43%. So that is greater than 41%. So that means we would check the plasticity chart. This is what their plasticity chart looks like. It's different than the Atterberg or the Casa Grande chart. So just remember that. What's the difference between these? The major one right here is that high plasticity versus low plasticity is at a 40% and a 50%. So they do that just to confuse us and make our lives difficult. So make sure you are reading the correct plasticity chart. This is AASHTO. And so same thing as before, it's right on that dividing line of 43% and 14 for the PI, the plasticity index, versus the liquid limit. So we have to plug it into the equation. This equation is a little bit easier. It's just a straight line with LL is equal, or LL minus 30 is equal to PI. So 43 minus 30, 14, and we see that we are again below, or sorry, yeah, the PI. That data point is at 13, so we are above that value, which means we are here in this region. We are above the A line, which means it's an A76. A76. So we have our group number, A76. Now what we need to do is also include the group index. And you remember this is empirically based, which means it's a horrible looking statistical equation. And from that, we have this equation, but there's these three cases. So if the soil is one of those 5, then our GI is 0. So that is our group index. If the soil, then we follow this equation, and if the soil is anything else, then we follow that gnarly looking equation down there. So in A76, that means, unfortunately, we have to use this equation. So we'll plug everything in. For this one, our F subscript is the percent passing, so they just use a different notation. And so for that, we can plug all of these values in, and we get a GI of 5.9. So what's the rule that we use for GI? What do we always round it to? Whole number, yeah. So A76 and then parentheses 6, that would be it. If you have a negative number, then it will always just be 0. Yeah, for this, like if you will not need to memorize these equations. Yeah, geez, that would suck. Yeah, you would not need to do that. Yeah, I did do that last time, didn't I? Yeah, I can do that. Yeah, I'll do that. Okay, so the last little question was, is this would you recommend this soil to be used as a roadway subgrade? As a roadway subgrade, the higher the GI number is the lower quality. So who remembers that dividing line for like recommended GI value? Starts with a 2 and ends with a 0. So any, like technically, it depends who you're talking to, like what, like each DOT is going to be different, but any GI number higher than 20 needs to be, well, we can't use it. Like there's too much fines in it. It's not going to be applicable. The issues with this is like frost heave and thawing and stuff, like change in volume during the seasons, like especially when it gets wet or whenever, freeze cycles come in. So for this, generally the soil is okay, even though that number is still high. Ideally we want to have a low number, like we want to have something in here, like or in here. But if you were comparing this and you had another A76 with a GI value of like 16 or something, then this one would be not bad, So this GI value, the group index, is only compares the same group number. So that GI value, if you had a A26 versus an A76 with the same GI number, then you want to choose the A26 since this is a better property, So this group number here can only be compared to other A76s. It's useless if you have 2 different group numbers and you're calculating the GI value. Okay, so USCS and AASHTO are the 2 major classification systems. Yeah. So there's an A8 soil in the author. Yeah, A8 is like, right, yeah. Yeah, for A8, you would usually try to get rid of it unless it was really deep, and then they might try to improve it. But A8's the worst one, and yeah, it's generally no go. All right, so USCS and AASHTO, those are the 2 like most common ones that you'll find just in your day-to-day stuff. Again, there are other classification systems. There's the USDA triangle, which is kind of stupid, but that might be on your FE or PE. There's another one that's like, I don't know, it's named after some guy like Burmeister. And I remember like seeing that on one of the PE study guides. I don't know if that's like a new and upcoming thing. I've never used it, but just again, there's these other types of classifications that you may come across in your FE and PE. But majority, these two are the ones used in your day-to-day work for typical projects. So some of the key distinctions between these two. The purpose for the USCS. This one is for structures and just general geotech. So anything that you are anticipating loading with a structural load should be using USCS. This includes bridges, signs, dams, and buildings. So there's still that overlap with your roadway. You know, like I said before, overhead signs, like toll gantries, bridges, MSC walls, although they make up a road, you still use the USCS. So the AASHTO is just for just the subgrade. So your general, like just when the only loading is going to be from a car or from a train or something like that. So DOT and FHWA only will use your AASHTO classification. So the options for AASHTO, there's 13 group symbols. For the USCS, there's a little bit more. There's 22 group symbols. And then the USCS uses group names where the AASHTO uses group index. So some people would prefer to use AASHTO because it's empirically based. So it's based off of the data and lab testing, where USCS is just based off of somebody making a flow chart and saying this is going to be the standard thing. So, you know, it's quantifiable. The AASHTO technique is quantifiable with that group index. The fine grain versus the coarse grain. This is a key distinction. For USCS, it's 50% passing the number 200 sieve. So whatever the majority is, majority of the weight. So if you have the majority of your particles are fine passing the number 200 sieve, that means there's 51% or greater, then we would call that a fine grain soil. For AASHTO, it's a little bit tricky. Instead of majority, which would probably be more intuitive, they use 35%. So if you have 35% passing the number 200 sieve, that means it is a fine grain soil. So although the majority of your particles might be coarse grained, they still label it as a fine grain if it's greater than 35%. The high plasticity versus the low plasticity, both are pretty like elementary still, but the AASHTO uses a 40% criteria and a plasticity index of 10. And then the liquid limit is 50% for the USCS. And then the plasticity index, they use a function to distinguish between high plasticity and low plasticity. So although the charts look very similar, you know, there's like a straight line and a bunch of like different types of lines intersecting it. They do have different key distinctions that you're going to have to know. Again, those charts will be provided to you in the problems. You won't need to memorize anything according to those charts, but you will need to know how to read each chart. Okay, further distinctions. That GI value is a function of plasticity and fine content. And then for the USCS, it's more adapt towards coarse grain material. So that is a function of the gradation itself. So the D10, D30, and D60. All right, any questions on soil classification? All right. Okay, so this was from your homework 3. This was a standard Proctor test. The Proctor test again is to determine the optimum moisture content of soil. Yeah.
Will the fourth one not be?
Oh, that was with the SBTs, wasn't it?
Yeah, it's that.
Yeah, dang it. I forgot to include that one, didn't I? I mean, you won't need to. You'll need to at least know the principles from that, but you won't need to memorize like those equations or anything. Yeah. So there's the other problem showing the SBT profile. The things you need to know for that is that the SBT n value is consistent of the addition of those last 2 blow counts, right? Because an SBT test, they hammer a drill bit into the ground 6 inches and they count the number of blows it takes to go 6 inches. and they do 6 inches, 6 inches, and 6 inches, so a total of 1.5 feet. And then the number we care about as engineers is the last 2 6 inches, the last 2 6 inches, so the last last total foot. And then we have to change all that for the energy and all that stuff. I will post the solution to that one. Sorry, I completely forgot that that one was on here. So I'll post the solution for that one so you can review that. But I think when I was looking through the homework, most people got a good grasp on understanding that. Okay. So yeah, this is the standard Proctor test. This is what we did in a lab from last semester, but it still has a geotech application to it. So what you would do, remember, you would plot these things. The dry, you would have to find the dry unit weight here, and then versus the moisture content here. And what we would see is that it would look something like this. And then the optimum moisture content, or the maximum dry density, is there. And then the optimum moisture content is the peak of that little curve. And that's an important property because that's the moisture content at which the soil can achieve its densest state. Again, thinking physically here, if the soil has too much water in it, then as we apply energy to that soil, the water is going to distribute the energy away from the particles. So we will not be able to achieve a dense state. If we have too little water, then the particles aren't going to be lubricated and they're going to be locked into place, and we won't be able to have that transfer of energy into compaction. So there's that optimum point, that sweet spot where there's just enough water, but not too much water, that will allow the particles to rearrange and absorb the energy, so we can have compaction. So with this, what we would need to do is find the weight of the density, the dry or the moist density, and then we need to correct that moist density for dry density. That's what we're plotting on the y-axis. The moisture content is then on the x-axis. So I don't actually show this whole process, but what you could do is just set this in Excel, calculate the density for each one, knowing that the volume of the mold is this right here, 1/30th of a cubic foot. All your other things are in pounds, and then always correcting it for dry density here. You would then plot that and find the optimum moisture content. You'd see that the gamma dry max is around 120 pounds per cubic foot, and the optimum moisture content should be around 11. So this is just looking at the curve. You're not actually setting a function or anything. So it's all based off of like, eyeballing it. So with that, then what we're asked to do is determine the void ratio and degree of saturation at the optimum moisture content. So this is where we have to go back to our phase diagrams and all that fun stuff and all those relationships there. And we know that this function here is going to be really important because it includes our void ratio as well as our specific gravity and our dry density here. So what we can do is solve for our void ratio here. And with this, I don't remember if I said to assume 2.65 or not in the problem statement. Okay, good. So you'd assume this, and then do not forget this one right here. We can find our void ratio that way. The void ratio should be about 0.378. Then after that, what we can do is find the degree of saturation using the George Soils Engineer equals George Washington or sewage or whatever it takes to remember this really basic function. Solve for our saturation, and we have a saturation at 77%. So this is a good check because if you remember, this curve here has a upper limit right here. That is our gamma ZAV, or zero air void curve. And when we have zero air voids, that means we are 100% saturated. So all the air voids are filled with water, and we got 100% saturation. So our saturation at this point should always be less than 100.
But we need to know
No, I think this one is given to you. I gave this to you on your first exam. Yeah. This one though, I don't think I'm gonna give that to you because that one we already, you should know that one by now. If you don't want to remember it that way, then you can know that gamma is equal to gamma dry times 1 plus W. That's like the same thing. And then you just rearrange those two. These are all based off of your phase diagram. So technically you could get, if you have this one, you could get to this by going through the phase diagram and taking out all the things. Go to permeability. Falling head permeability test was performed on a sample of soil in the lab. Total head fell from 49 to 28. So first, right off the bat, this is a falling head permeability test. So we have the two types of tests, constant head and falling head. What type of soil would we use a falling head test on? Who remembers? Close, opposite of sandy soil. So clay or silt, or just in general, low permeability. So falling head test is performed on something that is expected to have a low permeability, so something that doesn't let water pass through it. Constant head requires constant flow of water, so we need to have a higher permeable material, so like a sand or a gravel or something that lets water pass through it consistently. Okay, so we're given a bunch of other numbers here. We're told the numbers from the total head, 49 to 28, and the time, and then the specimen was compacted in a permeameter with an inside diameter of 8 centimeters and a length of 85 millimeters. So right off the bat, you're gonna have to change units so they're all the same. And the area of the standpipe flowing in the permeameter is given to you. So we're asked to determine the coefficient of permeability of the soil in centimeters per second. So our falling head equation is this one right here, and you will not need to memorize these, so don't worry about that. I can't even write it. So K is our permeability coefficient, shown as K. A times L divided by capital A times T times the natural log of our height 1 divided by our height 2. And that's where all of these things are represented here. So the capital A is the area of our permeameter, so larger area. Our lowercase a is the area of the standpipe feeding the permeameter. And the T is the time it takes for the head to fall from H1 to H2. So our H1 is our higher head. So H1 and H2 were given to us. Our time was 4.7 minutes, which is equal to this many seconds. Our L, the length it takes, is 85 millimeters, which is equal to 8.5 centimeters, just to get it all in the same units here. Our lowercase a was given to us, that's the standpipe, 0.45 centimeters squared. And then our capital A we need to calculate. This is an important step. Always make sure you have the areas here. So yeah, right here. Ooh, not red. Always make sure that this is in an area. So we have 16 pi centimeters squared. So what we can do then is plug everything in and make sure that our units are consistent. So our K value equal to 0.45, our lowercase a, right? Okay, 0.45 centimeters squared. Multiply that by 8.5 centimeters is length, our area, our capital A, I, meter squared, is our time, which is 282 seconds. And we multiply that by the natural log of 49 divided by 28. So make sure when you're using this in your calculator, you know how to go between log and natural log. Because if you put log there, then it would be completely different. So we do all this out, and what we see is a really small number, 0.00015 centimeters per second. Usually show it this way, times 10 to the negative 4 centimeters per second. So this is always a good check. These K values for falling head should be really small, right? They should be like decimal points in your centimeters per second. If you have a really large number, then double check all your values here. Just universally, we usually show permeability in centimeters per second. Just so, times 10 to the negative 4 is usually like a good fine grain that's still pretty permeable. Some of these clays are like times 10 to the negative like 8 and 12 and stuff. So really, really small numbers. So if you have a large number here, then most likely you forgot to transfer this area into a area, and you're still in like a length or something. Gosh. So always check those units and areas. Make sure you calculate the areas correctly. Again, though, you will not need to memorize that equation. That would be provided to you.
Like the
Yep, same constant. All right, this is kind of a fun, like practical equation or problem for permeability. We show this cross section of a levee. It's 200 meters long, and what we don't see out of paper, like coming out of the screen, is 500 meters. So it's 200 meters. Like we're working in 3 dimensions here. So this, I don't know, we can say this is X, Y, and Z. So our Y direction is 200 meters, but our X direction is 500. And the flow of water is measured in the collection ditch at 300 cubic meters per day. So we can measure this by like just the pump, like there could be a pump over here, and what is the pump rate that we need to have to keep the water level at a consistent level. This is like how an engineer would actually measure this in the field. So if they have to pump water out at this certain rate, then we can estimate that the water coming in is at that rate, to keep it at a constant elevation. So from this, we would need Darcy's law, which Darcy's law is what the permeability equations are all based off of. It's just a simplified version of that. It just says that the flow rate is equal to the permeability coefficient times the hydraulic gradient times the cross-sectional area. So for this, assumptions that we need to have. We need to assume, first and foremost, laminar flow. That's the most important. But you should know all of those assumptions that are associated with Darcy's law. So laminar flow is meaning that all the flow vectors are parallel to each other. There's no turbulence or anything. If we have that, then we can't use Darcy's law, and then we can't actually calculate this. So this is slow moving water. So from Darcy's law, Q equals KIA. Our Q is our flow rate, which is given to us in 300 cubic meters per day. Our hydraulic gradient is the change in head divided by the path or the length of the water traveling. So that would mean that the water enters right here at this ditch and then flows through here, through this soil layer, flows all the way out, and then comes out here. So that length, the water path, that L is 200 meters because that water molecule is traveling 200 meters. At one point, it has 190 head applied to it, and then at the exit point, it has 150. So it travels 200 meters. So we know the hydraulic gradient is 0.2. The hydraulic gradient is always in unitless values. So make sure that all of these units on the numerator and the denominator are equal to each other so we can cancel them out. So the A is the cross-sectional area to the flow. So for this, we have to kind of like think, looking at the not the profile, but the actual like other direction of it. So right here, what we would look at is the cross-sectional area would look something like this, right? Because this is coming out of our screen. So really this section looks like this. And that's what we have. We only have a profile for it. So hopefully this makes sense to everybody. We are looking at it profile, but then what we really need to look at it is this direction. And we have this 500-meter length levee total. So the area that the water molecule is flowing through is this entire area here, right? So it's going this direction in and out of the paper that way. So cross-sectional area is that, which is 1,000 meters or square meters. So what we need to find is our permeability coefficient. We are asked to find it in centimeters per second. There's different ways you could do this. You can convert everything ahead of time into centimeters or seconds, or you can calculate it and then convert it after the fact. So let's just do it this way first. Our Q, everything is in meters. So this answer will give us in meters per day, right? Because our Q is 3,000, is that right? Sorry, that's not right. It should be 300, so that's a typo. So it should be 300 cubic meters per day. We cancel everything out and then use stoichiometry to get it from meters to centimeters and then days to seconds. And then let's see. I don't know if this number is correct, if I calculated that with 3,000 or 300, but you would go through all these. And then what you should have is somewhere around this line, like centimeters per second. And again, double check here, like this is a small number, right? So generally laminar flow means slow velocities. So if we had a super, super high velocity here, then there must be some mistake somewhere. Like if we had something in like the 1,000 centimeters per second, like just think about that. Like that's pretty fast. Like, so this value being really small, you could probably like take a ruler and like count out the centimeters and you can picture the water traveling very, very slowly through that. So these numbers should always be small. So double check that. So yeah, again, you could do this in another way. I don't remember which way I posted the solutions or the shell, but you could also convert the flow into centimeters per second ahead of time. And then the hydraulic gradient, since it's unitless, you don't need to convert anything there. But you could also change the cross-sectional area into centimeters ahead of time and then do it out that way. So units are very important. And the flow path is important for this one, which is L. So know which way your L is going. Sometimes it's horizontal, sometimes it's vertical. It could be like at an angle. So you always need to find, like, think of what path the water molecule is taking, and that length is what you would plug in for your hydraulic gradient. Alles gut? Alles mir? Okay. So I'm not going to give you this. So you need to know Q equals KIA. Has everyone seen that in like your hydraulics class or anything? I know some of you guys haven't taken fluid mechanics yet, and this is kind of that area where there is like, this is the part of geotech that needs that. But really, it's only that equation. So Q equals KIA. It's easy to say. Q equals Kia. I don't know if you could they had hamsters driving a car, so you could remember it that way. The hamsters were cute, Q, I don't know, something like that. But Q equals KIA, and it works that way. All right. So flow nets. If you remember, we talked about flow nets. Flow nets are kind of antiquated nowadays. We use numerical modeling software that does this automatically, but flow nets will most likely be on your FE, and there was a question on the PE, and for now, we still need to know how to read these. It's a graphical solution to an analytical problem. So they are hard to draw. You're not going to need to draw them, but remember what the goal is to have them perfect squares. So you should be able to draw a circle in each one, and it should be a real circle and not an oval or a zucchini or a banana or anything like that. But obviously it's really hard to do that. Like this is, I'm not expecting you guys to draw these, but you will need to know how to read them. So for the flow net, this is our equation that gives us the Darcy flow. So this is lowercase q, so it's not a full flow rate, but it's a flow rate per like meter of dam. So our permeability coefficient is given here, and that's our K. So hydraulic conductivity is K. And all these other things make up that. So you won't need to memorize this equation, but you will need to know what the difference, how to find NF and ND is. So the ND is the number of equipotential drops, and that is taken from right here. So here is 1 drop, 2 drop, 3 drop, 4, 5, 5, 6, 7, 8, 9, and 10. So these are reading this way. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Make sure you know how to read those. What that is saying is that this head right here is dropping equally each point until we get to here. So at each one of these lines, we have an equal number of drops in head. So if we start at, what is this, like 6.3 meters of head, let's just say that this is our datum here. And we have 10 drops total. That means 6.3 divided by 10, so 0.63 meters of head is occurring at each one of these drops. That's what that is like physically telling us. So for that, our ND is going to be 10 from this. So our NF, how many flow paths do we have here? 3. Yeah, exactly. So that's showing this direction. So this is a flow path. This is a flow path. And then this is a flow path. So we have 1, 2, 3. And this is why we're assuming laminar flow. So laminar flow means these flow paths never intersect. There's no turbulence. A water molecule, if we were to put it right here, it would travel and never bump into another water molecule at a different area. It would be traveling laminarly. So what we have for our NF is 3. Our change in head H is equal to 6.3. And literally you can choose any datum you want. So even if you wanted to use down here as your datum, then that's fine because you're taking the difference between those two. But I think this is a better datum here. So we have H1 at, so you could just do 6.3 meters minus 0 meters. So this would be our H1 and our H2. So our permeability coefficient was given to us. That's our K value. Remember, permeability coefficient is the same as hydraulic conductivity. We just do that to confuse people. That's 4.2. Oh, sorry. 5.8 times 10 to the negative 4 centimeters per second. We would need to Yeah, okay. So we need to give the answer in cubic meters per day per meter. So we would have to remember that 100 centimeters is equal to 1 meter. And then that 800 or 8,640 seconds is equal to 1 day. So then you would do all this out, find K in units of meters per day, and then you would plug all this in to this. Since I'm running out of time, you would plug all this in. Remember that these are all unitless. And then this is in meters. So you would need to ensure that all your units are correct, and then plug in to find your Q. And that would be in cubic meters per day per meter length of dam. That meter length is coming out of the paper. So we're just looking at a little profile, a cross section of it. But then like the other one before, how we had like it was coming out of paper, like a total length of it. In this, since we're not given that, we just put it in cubic meters per day per that length. So then if we had a 2,000 foot long dam in this direction, or 2,000 meter, then we could find the total flow by multiplying that lowercase q times that total length. Does that make sense to everybody? I know it's kind of like counterintuitive because we don't see that dimension here in 3D, but think of this dam coming out of paper like it's a sub sandwich, and you just cut it in half and you're just looking at the profile of the chicken tender sub. Okay, go through this one a little bit quick. This is embankment fill required, blah, 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 all this stuff. There's 4 potential borrow pits. What I'm just asking you is for borrow pit 2. That's right here. So this requires an understanding of densities and void ratio and all that fun stuff. I give you the cost, but you don't really need this stuff for this problem. What we need to determine is the volume of soil required to meet the specifications of this embankment site. So the specification means at our project site, we need this much of soil, and it's going to be compacted to a void ratio of 0.75. So we need to determine the volume of soil from the pit. So from our source. So our source has a higher void ratio. If we have a higher void ratio, what does that mean? More loose, right? Yeah. So that would mean that we will most likely need more soil from this loose site, because then we're going to be compacting it into a smaller void ratio, which means it's more dense, right? So just right off the bat, like if our proposed site requires 6,500 cubic meters, and this is going to be in a denser state than our location where we're getting the soil from, then we're most likely going to need more soil to compact it into that tighter criteria. So this, we just need to remember that density is the weight divided by the volume. And what we need to do is determine the dry weight of solids at the embankment site, because the dry weight is what we're purchasing, and that's what we need to get from our site. So for that, our weight of soil that is required, and this is, I'm just going to put it in kilonewtons, to find that, we can then find our gamma dry and then the volume required. Oops. So for that, we need to transform this equation around. So we have the weight of the solid required is equal to the total volume times our dry density. So to get this gamma dry, I'm just going to say at our site. So this is the 6,500 cubic meters. The requirement there. We know that the specific gravity is 2.8. So what we would use is this equation, our GS gamma W divided by 1 plus our void ratio. This is equal to 2.8 times our unit weight of water in this unit, which is not 62.4, it is 9.81 kilonewtons per cubic meter. Then divided by our 1 plus our void ratio. At our project site, our void ratio is 0.75. So this means the required density at our embankment site is 15.02 kilonewtons per cubic meter. So now that we have this, we can find of solid required. Solid required. We know our total volume is going to be 6,500 cubic meters. That's from here. And then the density of that is going to be 15.02 per cubic meter. So the kilonewtons cancel out, and we have, or sorry, the cubic meters cancel out. 97,651 kilonewtons of soil is going to be required at our embankment site. So we have our site conditions. Now we need to determine how much volume is going to be required from our borrow location. So this is the mine, this is the quarry, this is whoever is giving us the soil. So for that, what I'm going to do is just label this as pit, our borrow pit. We use the same equation, GS gamma W, 1 plus our moisture 1 plus our void ratio. But now our void ratio at our borrow pit is 0.9, so it's in a looser state. So we can plug all this in. We have same density of water since we're in the same units. But now we're dividing it by 1.9 because it's 1 plus 0.9. So this the density at our pit is 13.84 per cubic meter. And let's just do a check real quick. This should make sense, right? Because it has a higher void ratio. We know that void ratio and density are inversely proportional. So the higher the void ratio means there's more voids, which means we have a lower density. So just comparing the two, since our site is at a lower void ratio of 0.75, we should expect to see our site to have a higher density. So it's making sense so far. Okay.
The GS for the first one.
Yeah.
Why is it the same as?
Because we're using the same soil. So we're taking the soil from the borrow pit, and we're not changing any of the material properties. We're not changing the mineralogy. We're taking that and bringing it back because the GS is the specific gravity of the solids. So it's the same mineral soil going from our borrow pit to our embankment. So we're not changing anything there. Okay, so for this here, let's just plug all these things in. Again, we're only looking at this one here. Our WS required is, so how much weight of solid we need is 97,651. Our density of our dry pit is 13.84. So that would mean the volume required is equal to our density times our weight, right? And that's just from this equation, rearranging it. Sorry, that's not right. Our weight divided by our density. Looks like a V. Our density. So we divide that out, and what we'll see is we need 61 cubic meters. And hopefully that also checks out and makes sense because we have more volume that we need, so we can compact it to a more compact state to get to 6,500. So if your number was less than 6,500, then there was some mistake somewhere in there because how could you have a lower volume and then compact it to a higher volume, you know? All right, moving quickly here. Seepage velocities. We talked about seepage velocity. This is using 1D flow here. This 1D flow is the same as Darcy's. It's just without the area. So the lowercase v, you know, this is technically the same as Q equals KIA, because if we multiplied each side by A, then we would get Q. So velocity times area is our flow, Q. So Q equals AV. So that's where that's coming from. But we're having a permeability here. And we're given this, what we need to remember is that, or what we need to find is the discharge velocity and the seepage velocity. So this is easy for this first part. This current V, this is our discharge velocity. So we can plug everything in here. K times A, which is equal to 4.5 times 10 to the negative 3 centimeters per second. Our I is our change in head over the length that it is flowing. So 80 centimeters divided by 0.65 meters. And then what we would need to do is convert this 0.65 meters into centimeters. So we know that, what is it, 100 centimeters is equal to 1 meter. And so all those units can cancel out then. We have centimeters over centimeters. So our velocity should be, our discharge velocity should be 0.0010. 55 centimeters per second. So this is our discharge. This is the water flowing out of the pore space into the open area. What we also need to find is our seepage velocity. Remember, the seepage velocity is equal to the discharge velocity divided by the porosity. We also know that the porosity is equal to the void ratio plus 1, or divided by 1 plus the void ratio. So we're given the void ratio. That means we can find our porosity. Should be about 0.31. So we would show the porosity normally in percent form as 31%, but whenever we're doing calculations, we need to bring it back into decimal form. So our VS equal to 0.55 centimeters per second divided by our 0.31. So that is 0.0177 centimeters per second. So that is our seepage velocity. So this is the actual velocity of the water particle traveling through the soil pore space. Okay, one more really quickly, because this illustrates the importance of the seepage velocity. Seepage velocity, we always need to calculate when we're thinking about sediment transport or contaminant transport through soil. So in this example, we have a tube with a known area, and it's 20 or 200 foot long, and it's filled with soil. And we want to know if a pollutant is introduced at point B. So right here, like let's say there was like a leak in this pipe or something, and some contaminated groundwater got into it. How long would it take for that pollutant to travel from point B to point C? So we know that it would be traveling a total of 150 feet, right? 200 minus 50 feet. So what we would do is use Darcy's one-dimensional flow. The discharge velocity is what we can find from Darcy's flow, but what we actually need is the seepage velocity. What's going on? Where'd it go? We actually need is the seepage velocity, which is equal to Vs divided by N. Just going to go through this really quickly. Find this, our change in head, here we have. Second. And then times our I, which is 25 feet, divided by 200 feet, since that's our total length. And we'll change that into feet per second, and that is 5.21 times 10 to the negative 5 feet per second. So our seepage velocity is equal to 5 feet per second divided by our porosity. Porosity is 0.65. Make sure that's in decimal form, not percentage form. And this is equal to 8 times 10. So the velocity is equal to distance divided by time. So that means the time, or let's see, so that would mean that seepage velocity is equal to the distance, which is 150 feet, divided by the time. So we would solve for time. And the time it would take to travel that would be equal to about 21.7 days. So units for this is important again, and understanding that the permeability, the total K here, the total velocity is using the entire length, the 200 feet, because that's where the two head measurements are. All right, this one is not that critical. This is the constant head test, compacted clay gravel. So it's just applying the equation for constant head. I think this equation, this is all given to you, right? This was in your notes, at least. So go through this step by step to find the discharge velocity. And then of course the seepage velocity is the same thing divided by the porosity. So for that, we would need to find our porosity. You can find the porosity by, understanding that the volume of the cylinder and then the weight of the voids or the total voids there, finding our porosity. Volume of voids, porosity is equal to 0.54, and then we can plug that in to find our seepage velocity. So go through this step by step, and if there's any questions on that, let me know. The additional concepts, subsurface investigation, this is going to be the heavy concept part. Understanding the sample methods, and then also the standard penetration test and the cone penetration test, the difference between those two. Remember, the big one, standard penetration test, we get a sample. So this is good. For cone penetration test, it's precise, but no sample. So we can't physically do any moisture content tests or anything like that. So to know the key differences between those two. For soil compaction, what is the goal of compaction? The method of compaction. So when would you use a sheep's foot versus a deep dynamic compaction, or whatever, deep versus deep dynamic compaction? So when would you use these two applications? And then the role of water content in compaction. So the relationship between those and optimum moisture content and stuff. Grain size distribution and plasticity. So how to read those two charts for USCS and AASHTO. And then the general like C versus hydrometers, the theory behind that, and then the plasticity Atterberg limits. So what is that based off of theoretically too? Any questions on this test? From 0 to 100, how does everyone feel? 70? That's not bad. If you guys, there's no labs this week, so if you have any questions while you're reviewing, let me know. Outside of office hours, I can hop on a Zoom, or you guys can come by my office and I can clarify anything in more details. But I'll see you guys bright and early Thursday.